Okay, welcome to the session on contributed talks to integrable systems. The first speaker today is Zhiyuan Wang of Rice University. He will talk about exact solution of a three-dimensional classical Ising model. Please.
Okay, so first, thank the organizers for giving me a chance to present my talk here. I'm Zhiyuan from Rice University. Today, I'm going to talk about a three-dimensional classical Ising model defined on a special 3D lattice structure, which becomes exactly solvable when some of its coupling constants equal certain complex values. And the exact solution is enabled by the transfer matrix method and the Jordan-Wegener transformation used to solve K-type Hohen-Kang model. To the best of my knowledge, this is the first exact solution of a three-dimensional classical statistical model that has a non-trivial phase transition, despite having some complex parameters. Later on, I'll comment on the physical meaning of these complex coupling constants and discuss the physical properties of this model uncovered by the exact solution, which include an intrinsic topological behavior of certain correlation functions. So let me begin with some backgrounds. As we know, one of the milestones of classical statistical physics is Ansar's exact solution of the two-dimensional classical Ising model, which is the first analytic solution that demonstrated a finite temperature phase transition. And here is the central part of his paper, where he presented the analytic expression for the thermodynamic free energy. And 20 years later, a much simpler solution was provided by Schulze, Matisse, and Lieb. And here is a sketch of their solution method. They first used the transfer matrix method to map the 2D classical Ising model to the one-dimensional quantum Ising model with a transverse field. And then they used the Jordan-Wegener transformation to transform the 1D quantum Ising model into a one-dimensional free fermion problem, which can be easily solved. There are many other exactly solved 2D classical statistical models, which are summarized in Baxter's classic book. Ever since then, people have been trying to generalize Ansar's work into the three-dimensional case, but this turns out to be extremely difficult, and the 3D classical Ising model remains unsolved up to now. Indeed, no one has ever succeeded in constructing a solvable 3D classical statistical model that is genuinely 3D, has real energy or positive Boltzmann weights, and a non-trivial phase transition. Here, genuinely 3D means that the partition function doesn't trivially factorize into product of decoupled 2D layers. As you can see from this summary table, to the best of my knowledge, our model is the first one that is genuinely 3D and has a non-trivial phase transition. So here is our model. It is defined on a three-dimensional tiling of the brick wall lattice, where the third direction has periodicity 3, and we only draw one period here. There is one classical spin on every vertex of this lattice, and there are spin-spin interactions only on the solid links. On the horizontal black links, the coupling constants are real, while on the vertical blue links, the coupling constants are imaginary, and the model is exactly solvable when these two conditions are satisfied. Later on, I'll comment on the physical meaning of these imaginary coupling constants, but let me present the solution first. So the goal here is to exactly compute the partition function of this model. To this end, we use the transfer matrix method. The transfer matrix is defined in such a way that the partition function is equal to the trace of the mth power of the transfer matrix. So the problem of calculating the partition function is reduced to computing the eigenvalues of the transfer matrix. And the transfer matrix for our model is written here. It is defined as an operator that acts on a two-dimensional quantum spin system, which is defined on this 2D brick wall lattice. And This structure clearly reminds us of K-type's Honeycomb model. The difference here is that in K-type's model, the Hamiltonian is equal to the sum of these three terms. Well, in our model, the transfer matrix is equal to the product of the exponential of these three terms. Despite this difference, the Jordan-Wigner transformation still works, which maps the spin-spin interactions into the Majorana fermion bilinears. So the next step is to solve the eigenvalue of this free fermion transfer matrix. And this is slightly more difficult than K-type's Honeycomb model because of the exponentials. The key observation here is that the Majorana fermion bilinears forms an SO2N Lie algebra, so that we can use the representation theory of this Lie algebra to calculate its eigenvalues. And here is a sketch of the solution. Basically, if we try to directly diagonalize this free fermion transfer matrix, that's going to be exponentially hard because the dimension of this matrix is 2 to the n, which is equal to the Hilbert space dimension of n fermions. What we can do here is to first map the transfer matrix into the fundamental representation of this Lie group, which is just 2n dimensional, and diagonalizing a 2n by 2n matrix is easy. And it turns out that there is a simple relation between the eigenvalue in the fundamental representation and the eigenvalue in the fermionic representation. So this is how we avoid the exponential difficulty here. I will omit some details, but here is the final expression for the thermodynamic free energy, which is simply proportional to the sum of all the eigenenergies of the fermionic excitation modes. And we can make a comparison to the 2D Ising case. We see that it has a very similar structure. The main difference is that the one-dimensional integral here is replaced by a two-dimensional one. So our exact solution allows us to exactly obtain the phase diagram of this model. It turns out that the phase diagram of our statistical model is quite similar to K-type's Honeycomb model. There is a third-order continuous phase transition that separates two distinct phases, a gapped A phase, an A phase where the fermionic spectrum is fully gapped, and a B phase where the spectrum has two gapless points. Now it is natural to ask what are the physical properties of the two phases in terms of the original classical statistical model. So here we have defined an order parameter that distinguish between the two phases, which is defined as a loop product of classical spins, product of spins around a loop. And it turns out that this loop product has a very interesting topological behavior. Basically, if we use periodic boundary conditions for all the three directions, namely putting the system on a 3D torus, then for shrinkable loops, the product of this observable on a shrinkable loop is equal to +1 for both the A phase and the B phase, while on non-shrinkable loops that wind around the torus in the X or in the Y direction, the exploitation value of this loop product is equal to 0 in the A phase, but equal to -1/3 in the B phase. So in summary, this loop product observable tells the difference between the A phase and the B phase and is sensitive to the topology of the loop. The exact solution also allows us to calculate some of the critical exponents of this model. For example, if we approach the phase boundary from the A phase, then the leading singular part of the free energy behave like this. It's proportional to the eta to the 5/2, where eta is the distance from the phase boundary. This confirms that our statistical model has a continuous third-order phase transition because the third-order derivative of the free energy diverge at the phase boundary. Now it's time to discuss the physical meaning of the complex coupling constants. The key idea here is that the partition function of our model can be interpreted as a quantum transition amplitude, where the complex parameters naturally arise from the quantum time evolution. So here, A and the initial and the final states are suitable product states, and the Hamiltonian for the quantum system is a Hermitian, locally interacting, completely physical Hamiltonian. So this quantity is completely physical. And this transition amplitude can be exactly computed at a special value of time using our technique. So in this way, the classical thermodynamic, the classical thermal phase transition we found in our model may be mapped to a dynamical quantum phase transition in the transition amplitude. I'd like to mention that our model can actually be generalized to a large family of exactly solvable 3D classical statistical models whose transfer matrix correspond to one of the generalized K-type models. And the family of solvable generalized K-type models has recently been classified by graph theoretical techniques. Sharpman already talked about this earlier today. And so this is really a generalization to a big family of models. We ask an open question here. Does this family contain a model that has only non-negative Boltzmann weights or real energy? So that's an open question here. And we hope that the recent classification of solvable spin models shed some light on this open question. And here is a summary of my talk. We have constructed a solvable 3D classical Ising model that has a continuous third-order phase transition. The solution is by a combination of the transfer matrix method, the Jordan-Wegener transformation, and the Lie algebra representation theory. We use the exact solution to compute its physical properties, including an intrinsic topological behavior of some loop correlation functions. We justify the unphysical complex parameters by interpreting the partition function as a transition amplitude, and the classical thermal phase transition we found may be mapped to a dynamical quantum phase transition of a certain quantum system. And we finally left with an open question about whether similar technique can be used to solve a three-dimensional classical Ising model that has non-negative Boltzmann weights. Thank you.
Thank you for this nice talk. Are there questions? Yes, please.
So, if at the end of the computation you just formally replace your complex couplings by real ones, do you get expressions for a free energy that admits a phase transition or not?
At the end of my computation, which slide are you pointing to?
So what I have in mind, is it possible that with at least formal rotation to real couplings, you get something in the universality class of the the real three-dimensional Ising model, or not?
I think that's a really good question, and I tried this, but up to now I haven't been able to find a transformation that maps this to a model with a real energy.
Okay, thanks.
Other questions? So, so is there a way to define magnetization, or like in the Ising model, to characterize the first-order phase transition? Or no?
Oh no, this is not a first-order phase transition. This is a third-order phase transition.
But is there a notion of magnetization?
If you we haven't computed the magnetization in this model. It's more difficult to compute in the exact solution.
Okay. Okay, thank you very much. And let's thank the speaker again. Okay, so we'll go over to the next talk by Harini. Are you there?
Yeah.
Okay, maybe you can share your screen.
Is it
right? So the next talk is by Harini Desiraju of the University of Birmingham, and she will talk about isomonodromic tau functions on a torus as Fredholm determinants and charge partitions. Please.
Okay. Thanks to the organizers for this opportunity. Okay, in the next 15 minutes, I'll try to summarize the main results of my paper with Fabrizio Del Monte and Pasha Gavrilenko, and here is the archive number. So our main goal with this paper was twofold. One was to explicitly formulate tau functions on a torus. I'll define what a tau function is in a minute. And then we wanted to make contact with Nekrasov partition functions. In this talk, my main example will be a torus with one puncture, but everything that I say is applicable to a torus with any number of punctures as long as they are Fuchsian. Okay, so this is my starting point. I'll start with equation of motion of a non-autonomous Collage-Moser system, which means that you have two particles in an elliptic potential, and the equation of motion is written in a center of mass reference frame. And this equation can also be seen as elliptic Penleve 6 with a very specific choice of parameters. In this equation, there are two main things to notice. One is that there is the parameter tau is the modular parameter of the torus. At the same time, it's also the isomonodromic time. Second is that there is this parameter n, which is in blue. So all the blue parameters will come from the equation. So you should just look for the color coding. Okay, and I'll also be calling the solution Q transcendent from time to time because it is transcendental in nature. So this equation has an underlying Lax pair. In other words, this equation can appear as a consistency condition of these two pair of linear differential equations. The Lax matrices A and B live on a torus with one puncture. The puncture is at z equal to 0, which comes from this denominator along with this particular matrix. So what I'm trying to say is that if you put everything together, you see that there is a simple pole at z equal to 0. The other observation is that A is traceless. Okay, so with this in mind, I want to now go to tau functions. So in the theory of integrable systems, tau functions have a very special role to play. They tell us quite a lot about the geometric and analytic aspects of the system. But for the purposes of this talk, it's good enough to know that the tau function can be seen as a generator of the Hamiltonian. This is not a unique definition, but it's one of the definitions. The Hamiltonian of the system in this case is the acycle integral of trace A squared, where P is the y-stress P function and eta is the Dedekind eta. So the tau function sits here. And the main question I want to address today is whether I can write this tau function as a Fredholm determinant. The answer is two-step. One is that tau function can be written in terms of the monodromy data of the system instead of in terms of a Hamiltonian. And this is true because of Riemann-Hilbert correspondence. But I'll not go into details. The second point is that once you have monodromy data, you can formulate the tau function as a Fredholm determinant. Now, why do I need a Fredholm determinant? There are many advantages. First thing is that when you see a Fredholm determinant, you know that there are other areas of mathematical physics that are connected, for example, random matrices. But what I'll show you today is very restricted to the system. First is that once I have a Fredholm determinant, I can write the transcendent, the solution of the equation, explicitly. By explicitly, I mean on one hand, you'll see the transcendent. On the other hand, you'll see some hypergeometric functions. Second is that when you have a Fredholm determinant, its minor expansion, in this particular case, will allow us to connect to Nekrasov open cofunctions. And here we find charged Nekrasov open cofunctions. And the word charge is because we are on a torus. So these pick up a charge. The determinant representation also lets us compute the connection constant in a nice way. In this case, it is also the same as studying modular properties of C equals 1 conformal blocks on a punctured torus. Finally, the distributions of poles of the transcendent are the same as studying the zero locus of the determinant. And studying zero locus is much easier problem than studying the distribution of poles. In today's talk, I'll show you the first 2 points, and the last 2 points are a work in progress. Okay, now I'll switch gears and I'll show you the construction of the determinant. The first observation is that the Lax matrix is multi-valued. So when you translate z by tau, it comes in with this extra factor conjugated. What does this mean? It means the following. When I have monodromy matrices, the A cycle monodromy is going to be just MA, I'll call it MA, but the B cycle monodromy will come with the same factor as above. So these two are the same factors. So the fact that the B cycle monodromy comes with this extra factor in front is because the Lax matrix is multivalued. The monodromy around 0, I'll call it M0. These matrices also satisfy the following constraint. This is a usual constraint on any monodromy matrices. On one hand, you have the monodromy around 0, which can be written in terms of the A cycle and B cycle monodromies. The explicit form of the matrices is in point number 2. What you need to notice here is that the red parameters are the monodromy parameters. In other words, A parameterizes the A cycle monodromy. A is here. Nu, the parameter nu, comes through B cycle monodromy. M, as I said before, is coming from the equation. And then there is this factor rho. This rho comes in as a symmetry parameter of the system. You can think of it in terms of background transformations. And the role of rho will become clear in a minute. So now there are 4 parameters in my system. 1 is coming from the equation, 2 from the monodromy data, and 1 is symmetry parameter. So the goal is that if I study the solutions, I need to get both A and nu in my solution. So I'm studying the most general class of solutions. So I went from starting from an equation of motion of Kolozsvár-Moser system. I told you about its Lax matrices and the monodromy data. Now, in terms of this monodromy data, I have to construct the determinant. And to do that, I will use the technique of Pan's decomposition. So if you cut the torus along the A cycle, which is in the red band in the picture, you get a sphere with 3 punctures, which I call pair of fans. Well, I don't call it, but it's called the pair of fans. So from a 1-point torus, I went to a 3-point sphere. And 3-point sphere is well known because it is the geometry behind hypergeometric functions. The monodromy group of the 1-point torus can be mapped onto the monodromy group of the 3-point sphere. And that is evident through this equation. So in other words, if I cut the A cycle, I get 2 circles that here are called C in and C out. The monodromy around C in, which is called M in here, is the same as the A cycle monodromy. The monodromy around C out is A cycle monodromy conjugated with the B cycle monodromy. And the matrix around 0 remains unchanged. Here, when I say the same, it is up to conjugation, if they're in the same conjugacy class. To this pair of fans, I can associate a linear system, which is here. If it looks slightly weird, it's because I'm writing it in cylindrical coordinates, and that's it. Okay, so there is an associated linear system to the pair of fans, and the remarkable fact is that y tilde here is simply the Wronskian of hypergeometric functions. As I promised before, at the end, I want to see the transcendent on one side and hypergeometric functions on the other side. So this is where this explicitness of the tau function is coming from. So now let's restrict y tilde to the boundaries C in and C out. And I'll call them y in and y out. And they're related to each other through a symmetry relation. there is sigma 1. Sigma 1 is a Pauli matrix. And this monodromy parameter nu is here. Okay, so in terms of these local solutions, which are hypergeometric, let me define the following determinant, where K11 has the following kernel. It's a block operator. It's a 2 by 2 block operator. And this is the explicit form of the kernel, where A, B, C, D, you can see them here. And everything is in terms of the local solutions. Now, the structure of this determinant is a generalization of the construction by Pasha Gavilenko and Oleg Lisovy on a sphere. They did this for Penlevé 6 and Garnier system on a sphere. And then we generalized it to genus 1 surfaces. Now, if I take the logarithmic derivative of this determinant, it spits out the Hamiltonian and a bunch of other terms. In the bunch of other terms, there is A, the monodromy parameter, and rho, which is a symmetry parameter. So this is very explicit. On the one hand, there is the Hamiltonian. On the other hand, there is a determinant along with some other factors. So it's explicitly, we can write it explicitly. We can study different characteristics of this determinant and so on. But the important point is that changing this rho and taking the ratio of the determinants, I can understand what the transcendent looks like. Although it is embedded within the theta functions, the expression is completely explicit. So in this sense, the determinant is the true tau function of the system because it relates to the transcendent. And this relation should be very familiar for the experts who know something about Penlevé 3.3, for example. This is a very similar kind of expression you get there, where you have this determinant and you shift it by some backing transformations. Okay, now to the second point that I promised, which is the relation to the Nekrasov partition functions. Any Fredholm determinant, in general, if you take the minor expansion, the minors are labeled by some partitions. Now, the difference here is that since we are on a torus, you get extra factor in this way of labeling minors with partitions. And that's where the charged aspect of this partition comes in. So this charge kind of picks out what minors will contribute to your expansion. And this is the expansion of the determinant, where the minors are sitting here. These are the minors. And this is some extra terms that come in. These minors are basically the conformal blocks. And they also lead to Nekrasov partition functions. And as I said, this charge is related to the fact that you have some B-cycle monodromy. It is explicitly due to the B-cycle monodromy. And this is the full expression. So you have the tau function in terms of the Hamiltonian on one side. Oh, sorry. In terms of the Hamiltonian on one side. On the other hand, sorry, I can't. Okay. Anyway, these factors came before. Just look out for, one more thing is that whenever I say A, this is just A comma minus A. So wherever there is a vector, that's what I mean. So if there is Q, this just means Q minus Q. Okay, so it's extremely explicit, and Z_pert and Z_inst refer to the perturbative and non-perturbative parts of Nekrasov functions, which are just combinatorial objects, which I'm not writing here because they're really long expressions. So I started from the determinant, I took the minor expansion, and I showed you where the combinatorial structure comes from. Now, it wouldn't be, it is easy, or it is at least logically possible to see that all that I said up to this point can be applied to an endpoint torus. So you have the same Pan's decomposition. Each pair of Pans comes in with hypergeometric functions. Everything is very explicit. I want to also emphasize that the determinant that we get for an endpoint torus is very beautiful. Beautiful in the sense that there is a sphere tau function sitting right inside, which I want you to, if you want to see, this is the archive paper. Okay, I'll conclude my talk. I showed you how to formulate these tau functions. I showed you that we can rigorously establish a connection to Nekrasov partition functions and to C equals 1 conformal blocks. And here are some works related to what I just said. Thank you.
Thank you. Questions? So I have a question. So this is the Nekrasov partition function for some special value of the omega background, right?
Yes.
Can you go away from that point? Can you perturb it somehow?
Yes. So if you perturb it, it should actually coincide with the results in this paper. So they should be related to some quantized version, but yeah. So
would it be related to the quantum Calogero-Moser system?
Hopefully.
Okay.
It's a work in progress.
Okay. Thank you. So if there are no further questions, let's thank the speaker again. Okay, thank you for these nice talks, and with this we will close the session. Bye.